And we're back. In the last video, we introduced this notion of a priority queue, which supported the following four operations. You could check if the priority queue was empty, we could add to it, we could peek at the minimum value, we could therefore find out what the minimum is, but we could also remove the minimum value, and those are the only four operations my priority queue supports, and because there's only a few operations, I can be clever about how I implement it, how I represent it internally in the computer. So here was an example where we added the values 8, 2, 3, and 5, and we said there could be duplicates, but there aren't in my example. And from the outside, we're not going to worry about what order they are stored in, as long as we can find out what the minimum is and remove it, and add to it, of course, again. But internally, we took a look at representing it, first using an unordered dynamic array, where we just stored the values in whatever order we chose, and we discovered we could add to the end of that, making a new box in our array in constant time. We could find the minimum value in linear time. That would involve looking through the entire thing for the minimum value. And then removing the minimum value would take us linear time, because we'd have to search through the entire array to find the minimum. But then we could actually remove it very quickly by plugging the minimum value, replacing it with the last value in the array, and then removing that last box in constant time. But overall, removing the minimum took us linear time. And we wondered, how could we do this faster if we had if we had the same unordered dynamic array structure, but we also knew where the minimum value was. We kept track of the index of the minimum value in our priority queue. So here we have the same values in our array structure, but we also know that the minimum value is at index 1, where sure enough I see that 2 is the minimum value. I want to know, how does knowing the index of the minimum change the running times? Well, let's see. Let's start with peek at the minimum. How long does it take to find the minimum value? Before, we had to loop through the entire array to find the minimum, but now of course we know the index of the minimum. It's 1, so we can just use the power of arrays, jump right to the value at index 1 in constant time, find out that it's 2, and return it. So that's going to be constant time. Excellent. Now how long does it take us to add an element? Let's look at add. Now we can still add to the end, right? Let's suppose that we add the value. I don't have much room, I realize now, to add values, but so we'll try adding the value 7. So we'll just make a new box, write 7 in it. That would be box 4. And sure enough, we've added a value. That appears to be constant time, right? But wait a second. What if, let's go back in time, what if I hadn't added 7? What if the value I added was 1? Why is 1 more interesting here? Because if I add the 1, I also have to change index of min, because the minimum value is no longer at position 1, it's now at position 4. So index of min should be 4. What do I have to do in order to... So let's see, I can add the value in constant time. So let's see, add in constant time to the array, but adjust index. How long does it take me to adjust the index? Let's see. All I need to do is compare the value I'm adding to the value at the minimum. I can find the value at the minimum in constant time. We already know that. I can compare it to my value in constant time. If I discover my value is greater than the minimum, like 7 was, nothing else to do. If the value is lower than the minimum, then I simply need to do one other constant time thing. I need to update index of min to be that index. So I didn't have to cruise through the whole array. I just needed to compare the new value with the value at the minimum, and I already knew where to find the value at the minimum. So I can adjust the index. That's also constant time. Therefore, overall add is constant. How about removing the minimum value? Let's see. I can find the minimum in constant time. Right now it's over here, although now I'm kind of sorry I did that. So let's go back in time to when it was at position 1. So let's pretend this was a 7 again. So I think that will be a better example for removing the minimum. So to remove the minimum, what do? Well, I find it in constant time. I just look, index of min is 1. I look at that index. There it is. The minimum value is 2. And to remove it, I'm going to plug that, just like I did before, just like we did up here. We'll remove it, by plugging it with the value that is in the last position, which is now the 7. And that means we no longer need this last box. Plugging it with that 7 is constant time. Removing the last box should be constant time, knowing how an array list or other implementations of a dynamic array work. Therefore, I can remove the minimum value in constant time, right? Oh, but wait. Something's wrong with this picture now. The minimum value, once we replace this with the 7, let's do that. Replace it with the 7. The minimum value is no longer at position 1. Where is it? It's at position 2. Right? It's this 3. That's now the lowest value. How do I know that? Well, I'm going to have to cruise the entire array to find the new minimum. So here, find the minimum is nice and fast. Remove the minimum is nice and fast. I think there should be a big O over here. But update the index is now really slow. We're going to have to cruise through the entire array looking for the new minimum. That's going to take us linear time, and eventually we'll update it. In this case, it's now the value 3, which is at index 2. So overall, removing the minimum is linear time. So where did we get to? We originally had constant linear and remove was linear. When we introduced the index, that gave us still constant, but now constant linear. So this is a win. We made peak min faster. We're not disappointed in that. Let's try another way. So here we go. Representation number 3. If we're concerned, if we want to beat this linear time for removing the minimum value, we might think that the best way to do that is to not have to search so hard for the new minimum. We don't want updating the index to take linear time. One way of making finding the next smallest and then the next smallest value a nice quick operation is to keep the data in sorted order, which you might have guessed was coming since the fact that I keep emphasizing it was unordered before, so now it's ordered. So we'll say dynamic array. I'm putting dynamic in parentheses because I think array is really the key idea. So if you're uncomfortable with dynamic arrays, you can still understand running times in terms of the array itself. A dynamic array in increasing order. Okay, so now we don't need that index anymore. Let's take a look at what that might look like. So again, we'll have some boxes. I think my original values were, what, 8325, is that right? 8235. But this time, because it's in increasing order, they'll be stored as 2, 3, 5, 8 in increasing order like that. And again, we want to figure out what is the running time of each of these key operations, assuming that we can determine if it's empty in constant time, which was the 4th operation we had before. Okay, how long now? In fact, let's clear that stuff temporarily so we don't have to think about it. How long now? Well, peek at the minimum. How long will that take? That should be constant time, because what are we going to do? We're just going to return the first value. We can do that in constant time. The first value is going to be the minimum value because the data is stored in increasing order. How about removing the minimum value? Let's put that one aside for a moment. How about adding? How do we add? Well, now we have to insert, right? It's not just enough to add the value to the end, because, you know, if let's say we're adding 4, 4 doesn't go at the end. If I add a 4, let's do that. That means I need to shift the 8 into that last position. Oops. Shift the 5 over. So I now have room for the 4 so that I maintain the array in increasing order. So here's a reoccurring theme here. When I decide to store, I'm stricter about the kind of information I store, like I keep track of the index of the minimum, or I force my array to be in increasing order because I want some operations to be faster. I now have added maintenance work. Like here I had to update the index in representation number 3, where my array is in increasing order. I need to make sure it stays in increasing order, and that's going to add to the running time. So how long does it take to add? Linear time, because I need to maintain the order. I need to shift the elements to make room to add the element I'm adding. I shifted 5 and 8 to add 4, and potentially I might need to shift all of them to add 4. So therefore, potentially linear time. How about removing the minimum value? Well, the minimum value is easy to find. It's the first one. So find in constant time, but removing means shifting all of the values over, right? If we remove the 2, that means we can't just plug the 8 like we did before, take the last value and plug the whole. Now we remove the 2, we're going to shift the 3 into that position, shift the 4 here, the 5 here, oops, 5, whoa, 5, get over there, and, oops, I think I'm hitting the wrong key here, 8, and now we can get rid of that last box, and we've successfully removed the minimum. So every time we remove the minimum, everyone has to shift down, and that seems unfortunate. Now we have we have linear time because of the shifting. So, in summary, linear, constant, and remove minimum is linear, even though we could find it very quickly. So to compare, that means previously the best we had done was keeping track of the index of the minimum and having the data in no particular order. That was constant, but remove min was linear. Now we're worse. Add is linear and remove min is linear. Well, that's disappointing. So before you click on the next video, you might think about how could we take this idea and improve upon it so that we can get rid of some of this linear time and see more constant time. I'll see you in that next video when we explore representation number 4.